Hello everyone, today we are going to perform a modal analysis with FEniCSx. Since a lot of you were curious about my last analysis, the Corvette modal analysis that I showed both here on YouTube and on LinkedIn, we are going to make that specific modal analysis. So let's go. Let's open our VS Code. Then let's create a new Python file. Let's call it modal analysis.py. Before starting, I want to show you this Corvette mesh. So let's open it with Gmesh. Let's go into our folder. Let's wait while it opens. Okay, let's turn on the 3D elements. And as you can see, this is the mesh that I built from the Corvette CAD model. So you can see the car cabin, you can see the seats, kind of, and we are going to make a simple modal analysis to extract the resonant frequencies of this cavity that can be used for a modal superposition if you want. If you just want a modal analysis output, we will have both the list of modal frequencies and then the modal shapes, that in this case will be a 3D scalar field. Okay, so let's start. So modal analysis compared to a regular analysis uses the SLEPc module instead of the PETC one. So the first difference is that we are not going to define the bilinear form and the linear form just like we did in the past videos, but we are going to define the stiffness matrix form and the mass matrix form that have to be assembled respectively in the stiffness matrix and the mass matrix. Okay, and let's see how it's done. First thing, I'm going to write out all the modules needed in just one step. So let's go ahead. So let's go ahead and let's import our mesh. just like the last time, I'm not going to explain everything. This is just identical to the previous video, so I'm just copying the command. My mesh file is named corvette.mesh. Okay. I forgot to import the MPI module, so I will do it here. Okay, now let's set air parameters. So it's just the air density and sound speed. Let's define our function space and test and trial functions. So let's set the polynomial degree to 1 for now. Of course, just like I said before, for acoustics and in general, it's way better to, coarsen a bit the mesh and then higher the polynomial degree at least to 2. So the accuracy tends to be way better in this way, even if you get, of course, a higher computation time. So for now, just set it to 1. Let's define the function, the trial function. And the test function. Now it comes the big difference with the previous case. And here we are going to define the stiffness form and the mass form. So basically we are going to assemble separately the stiffness part and the mass part. So we are first going to define the stiffness matrix form using the form function and writing the same integral that we wrote last time. So the one, you should know that the acoustic stiffness comes from the first integral that contains the gradient functions. So we have grad view, and gradient of v times dx. The same thing can be done for the mass matrix form. We just have u times v times dx. So we have them, and now we can assemble the matrices just with the command assemble matrix, where we give as input our forms we defined above, and then we have these empty brackets in which we would put the Dirichlet boundary condition if we had one. In this case we are simulating an empty cavity, an air cavity with rigid walls and no Dirichlet boundary conditions. So we also define and assemble the mesh matrix. And then to finalize the assembly, we have to give call the function assemble for both matrices. And then we are done. So this is basically what FEniCSx does. You know, by default, you don't see this. This is done under the hood, but basically is creating the forms, assembling the matrices, and then creating, in that case, a PETC solver with your specific settings. But they don't have an automatic model analysis tool, so we have to assemble manually the matrices, and then we are going to create our SLEPc solver. Let's go ahead and let's set up our eigensolver. We imported from SLEPc this SLEPc module, and we are going to use it. So let's define our problem. So our solver, let's call it solver, and we will use an APS solver. This function initializes an eigenvalue problem solver. Then let's go ahead and we are going now to give our solver a lot of settings. So the first one is the number of modes that we are going to extract. So let's call the set dimensions function. Let's give it an input that is the number of modes that we will set, just as an example, to 20. So we are going to extract the first 20 modes of the cavity. Then we are going to set the problem type. So in this case, we are going to use a general Hermitian eigenvalue problem. So let's call it in this way. This is a general Hermitian eigenvalue problem. Now we are going to initialize our spectral transformation module. So let's do it. We are going to set the shift and invert algorithm. We are going to set the shift to 0.1. And then we are going to finalize setting the options. Let's assign this spectral transformation to our SLEPc solver. And then let's assign to our solver the operators that are just the stiffness and the mass matrices. Then we can finally solve the problem with a simple command. And it's done. So once the solver ends the computation, we can get a lot of data from it. So first of all, let's initialize the real part and imaginary part of our eigenpair. So let's create with the function createVex. That is just initializing these two variables to vectors that have the same sides of the matrix K. Then we could be interested in the tolerance of the solver and the maximum number of iterations that it got, and we have a function for this. So put solver dot get tolerances. We can get a lot of other variables and information about our modal solver, but I'm keeping it quite easy and minimal. This is a minimal tutorial. You can also get stuff like the number of converged eigenpair, but we are not using it right now, so let's go ahead. I'm copying a pretty standard set of print statements. Let's just change problem with solver, where we will get the number of iterations that we just extrapolated from here, the solution method, and the stopping condition that is taken from this data here. Okay, then we want to print the eigenfrequencies, and so let's do that. I just forgot to put and extract the number of converged eigenpairs. It's pretty easy. The function is this one. So we can start printing out all the eigenfrequencies. Of course, we are going to do it after initializing the eigenvector array and the eigenfrequency array. And now we can print the eigenfrequency. Of course, we are going to do that just if the number of converged eigenpairs is greater than 0. So we can start a for loop for the index I in the range of number conv. We will first of all extract the eigenpair. So this function basically takes in the input I and will put the eigenpair into the real and imaginary part of it. Okay. Then we will define and compute the eigenfrequency for this value of the index. Of course, we are considering the real part of the eigenvalue divided by 2 pi. This is just a basic formula that links the frequency to the wave number. So let's append such a frequency to our array. Oh, I made a mistake, I don't know why. Okay, let's print out the eigenfrequencies. And then let's append the eigenvector to the eigenvector array. This is it. Okay guys, I just noticed that I made a mistake here. Of course, I was missing the function space inside the test function. I'm sorry. Let's run the script. Let's wait until it completes. And as you can see, we just got all the list of the first 20 eigenfrequencies. And this is it. So of course my advice is to, work on your case accuracy, maybe augmenting this to a second degree polynomial. This is just for demonstration purpose. You can do all the sensitivity analysis on your problem. But another interesting thing can be to visualize the mode shapes of our problem. So let's do that for all the eigen value that we found. So let's make a similar for loop. So let's open an XDMF file. I will just use the same module of the last time, so you can just copy it. Let's call it mode underscore, and then we will put we will put the eigenfrequency number, but let's round it maybe. So let's use a string. Let's round the number of the eigenfrequency at the index I. Okay. Then we will add also hertz in the name, of course, .xdmf. Let's set the write mode, and then let's complete it. So we will define a function u in which we will put our eigenvector values, so our mode shapes. This is done with the vector function in the FEniCSx function. We can just assign it like this. Let's give it a name. And let's write first the mesh and then the function. And everything should be fine. So we can run the script. Okay guys, I noticed that I made a mistake. Of course, you noticed, before I could do that. It's round to... Let's run the script and let's see how the mod shapes are exported in the XDMF format. As you can see, the mods are being exported, and now we can visualize one of them in ParaView. Okay, let's open ParaView. Let's go in our working directory. Let's open one of the mod shapes in XDMF file, in XDMF format. Oh, I will choose just a random one. And this is it. We completed our modal analysis with FEniCSx. So, just as an example, you saw my video maybe last week, and usually I like to see 3D fields like a sound pressure field, or maybe a mod shape field, like in this case with contours. I think that 3D contours are a better way to display a 3D field like acoustic one, both in case of sound pressure and mod shape. So let's select our contour function. Let's add a range. Of course, in this case it's automatically calibrated on the available values. Let's put 20 as a number of isosurfaces. Let's generate it, and we have it. This is basically how I do my visualization, at least in the starting phase. Maybe you can change the color. Maybe rainbow desaturated is what I tend to prefer. Maybe you can also, change the lighting, give it a little bit of specular power. Then you can change the type of interpolation, the PBR. It's way more cool in my opinion, and just move these parameters until you don't get your desired visualization. This is it, and this is how I managed to perform the modal analysis on the Corvette that you saw last week on my YouTube channel and on my LinkedIn profile. So, if you want to know more about acoustic, vibroacoustic simulation, modal analysis, direct frequency responses, thermal vibroacoustics, don't hesitate to write me. Subscribe to this channel and follow me on LinkedIn. See you in the next video, and thank you for watching.